Welcome back to Two Minds, One Model, a podcast dedicated to exploring topics in machine learning and artificial intelligence. I'm John Jezel, along with my co-host, John Rocha, and we're here at Sonoma State University's Department of Computer Science. This episode, we're diving into more fascinating AI research on this semester's main theme, interpretability. But first, some AI and ML news. OpenAI and AMD have sealed a multi-billion-dollar agreement to deploy 6 gigawatts of AMD chips. That's roughly 7 San Francisco's worth of power for future AI data centers, with the first deployment of AMD GPUs scheduled for late 2026. This partnership demonstrates OpenAI's willingness to hedge their bets against NVIDIA's dominance in the AI computing sector. OpenAI is reportedly laying the groundwork for an initial public offering that could value the company at up to $1 trillion, with plans to file with securities regulators as soon as the second half of 2026 and raise at least $60 billion, making it potentially one of the biggest IPOs of all time. The IPO preparations have come after the company completed its corporate restructuring to a public benefits corporation on Tuesday, with CEO Sam Altman stating during a live stream that going public is the most likely path for us, given the capital needs that we'll have to finance his plans to pour trillions of dollars into AI infrastructure. A grieving family used Claude AI to slash a $195,000 hospital bill to $33,000. The $20 a month chatbot subscription helped identify $100,000 in duplicative charges alone. In the last episode, we explored an Anthropic paper on decoding superposition using dictionary learning as a follow-up to the preceding episode where we presented superposition and polysemanticity. We discussed how researchers use sparse autoencoders to extract interpretable features from a 512 neuron tiny, or petite as we settled on, model. But here's the worrying question. Will it scale, or was this just a parlor trick? In today's episode, we'll look at the results of researchers applying these techniques to Claude 3 Sonnet, a real production model millions of times larger. We'll look at the challenges they faced and what they found. How did they attempt to validate that they really accomplished what they set out to do? And ultimately, we'll review the technical breakthroughs, implications, and limitations they presented in scaling monosemanticity, extracting interpretable features from Claude 3 Sonnet. So let's get started.
Yeah, and to be clear, Claude 3 Sonnet is Anthropic's mid-size production model. I don't know how many of you interact with these tools past the web interface, but typically the web interface has 3 front-facing models, a tiny one, medium-sized one, and a large one.
Editor John here. When John says tiny in this context, he is not in fact speaking of the tiny models which we have dubbed petite in the previous episode or later in this episode, because that's not at all confusing. Thank you for your attention, and carry on.
In Anthropic's case, the smallest is called Haiku, Sonnet, and Opus. For GPT, the naming scheme is actually all over the place, and actually GPT-5's issue was that they tried to be fancy and do automatic routing. Did any news about the GPT-5 release filter down to your circles? Sure. Or
yeah, I've spoken to people about the auto routing feature functionality, maybe we'll call it, of the new GPT-5.
And essentially, many people did not enjoy the update that OpenAI pushed and called GPT-5.
That seems like an understatement.
Yeah. One of the feature changes that they made that was a large portion of why so many people were unhappy is that model routing. In an effort to save compute, basically, instead of letting the user accidentally or purposefully demand the largest model, the biggest budget of compute for their query, what is 1 + 1, let's instead have a small model analyze the likely difficulty of the query and let that model dictate which size model that query gets passed to for actual answering. Obviously, they have an incentive to keep your query as computationally cheap as possible, and that had the effect of making the results much worse, because instead of, as a user, you would rather overshoot and burn their compute than undershoot and get a wrong answer.
Right. As a user, I want the best possible answer.
And they, as a company, want to provide you the right answer, but as cheap as possible.
Sure. It's kind of maybe a tangent. Look at us. We're going on a tangent.
Yeah. Oh, yeah. I forgot this is completely unrelated to the topic at hand today.
But while we're on this tangent, and maybe pull it back to some things we've discussed in previous episodes, are there some parallels between the routing that they're doing and the concept of mixture of experts?
Kind of.
Yeah.
In the sense that, kind of.
Yeah.
You're right that they're both architecturally about splitting and routing. They're both architectural changes to the routing of the input data as it passes through the network. However, in Mixture of Experts, it's about only letting a subsection of the neurons in the model fire at any given pass through the network. Mm-hmm. So it's one model constrained artificially to only use an eighth of its brain or whatever, and 1 over n of its brain at any given forward pass. That reduces computational cost of activation, and it has some interpretability benefits that continue to be explored in different research endeavors. This is more, back to full circle, this is more mechanistic interpretability, which is like a different subfield of interpretability. But yes, it is very similar from an abstract where they're approaching the problem sort of way. Okay. But back to your question, was this just a parlor trick? How well does it scale?
Well, that question.
Right. The small question. So just to give you an idea of scale, we're going from a 512 petite model to one with approximately 8 billion neurons. So yeah, that's about, I think you said, 1 million times increase. See, if I was good at this, I would have remembered exactly what you said.
Yep.
But 15 about a 15 million x
not
increase.
Quite a million, but
only an order of magnitude.
It's within the order of magnitude.
Yeah. We both have been surprised many times at the numbers that illustrate how much these endeavors are scaling computationally, ambitiously, budget-wise, CapEx. I've seen videos running a 500 billion neuron model on your home rig.
Right, on your home system. Yeah, that's crazy.
So yeah, back to Claude Sonnet. So that's to give you an idea of the size we're dealing with. We went from 512 neurons and 4,000 features to roughly 8 billion neurons and 34 million features. That should give you an idea of the step up in scale we're taking here. Many researchers thought that SAE simply would break at half the scale. We're taking the step up here. Or they just didn't want to spend the money to find out. That's a different question. But there is a relationship between features and the neuron count, and we'll get more into that as we discuss the architecture here of the experiments and whatnot. So let's dig deeper into the scaling challenge, the reason or some of the numbers behind why this is such a computationally expensive endeavor. Detangling superposition. Superposition, as long as it's been an issue, has been investigated by researchers. In all of those domains, scaling is one of the big Goliaths that the researchers have to conquer. Because no matter what, we joke about, OpenAI has 800 million weekly active users, and I think they lost something like double-digit billions in the first half of this year.
Of dollars.
Right. So this scaling is an omnipresent force here. So there was a lot of expectation that this approach would not scale to production models, but this is one of the first methods that did actually scale to production models. And in fact, it went kind of viral in the spaces that care about this stuff for the Golden Gate example we'll talk about later. Not only did the size of everything scale up, the size of the training corpus scales too, in case you think we forgot that. We're talking about single-digit billion training tokens to trillions of training tokens. Mm-hmm. We're talking a production-level model that they charged and users paid money for. So this was a full-scale, deployed, serious, human feedback-taught model. This is no longer a toy or a endeavor to write a paper. This is a serious R&D effort. So the training data scale vastly increased. This means things like web, texts, code, any language you can think of, even less common like base64 data is vastly more represented, and thus the features related to those things expand too, as we'll see. Features that were simple become more complex features as the model gets bigger. So feature density is also a problem. If the idea of the fact that a language model might be aware of its existence and the fact that it's being trained, if that's an idea that's only present once every billion tokens of training text, that feature is going to be hidden very deeply down in the geometric organization that we call superposition, the way these models store more features than they have space to store them. The density of features is a problem in the sense that if safety features are rare, monitoring for their behavior with this architecture is fundamentally difficult. It's fundamentally difficult because the more infrequently data arises in training, the more obfuscated it is in the internals of the model. So it's bad from all directions. And then you have the whammy of, your normal solutions for it being bad at something would be give it more examples. But that's kind of the exact opposite of what we want to do here, too. We don't want to increase its ability to do bad things in an effort to find its ability to do bad things. So the normal way that we would solve this issue is just make it better at the thing, and that requires more training data of that thing. And we can't do that either because, shocker, it learns the wrong thing. So, yeah, feature density is also a major bottleneck that was considered an obstacle and was top of the list when investors were turning down research leads, or however R&D goes at a premier lab. Then there's the notion of, okay, this sparse autoencoder can characterize 34 million features of a model you have in production. Cool. Are the features the ones we want? Are they good? Do you have a million different behaviors about talking about dogs? How highly abstracted are the features? How good will they make us look to VC firms?
Venture capitalists.
Right, yeah, VC firms. How cool will they look in a New York Times headline? A few of the ways that the features discovered with these sparse autoencoders are classified as good or useful features is that they sample the top activating examples for each feature. That is to say, they don't bite at the hook every time there's any activity in the network when looking for where the network activates. They wait until the network really activates somewhere before they jump on it and attribute that activation to a behavior. It's just like, what's the coherence rating on the signal, kind of. That's one method. Then another is to, shocker, use an AI to recreate the pattern. That is, sparse autoencoders fundamentally reconstruct the behavior of a model as the information flows throughout it. It does this by sampling kind of the highway between compute blocks, called the residual stream. This information that is in this highway bus, you could call it, accumulates the effects of each layer on the input data. And that's one of the differences. In the last paper, they sampled a single layer's activations as time-stepped information. Here, they look at what's on the information highway, what's being passed from layer to layer in between each layer at the middle block of the network. You might ask, why not look at it near the end? If you look at it too near the end, you get way too many results that are about formatting or how to answer things. And if you do it too early, you get something too close to the input. So you want to sample the network in the middle of its processing of the input to get the best signal, because what we're trying to do is compress the activation of the behavior of the network into a smaller model. With incurring less computational cost, we can more easily categorize and map the behaviors of production models to discrete circuitry or spaces of neurons in the brain of the model. So you can use a neural network to reconstruct the behavior from the sparse autoencoder into the actual behavior that Claude does during activation. You can test to see with new data. Like, let's say you want to test how well you've mapped out the model's knowledge of something iconic like the Golden Gate Bridge. If we get a new piece of data, a new user query that mentions the Golden Gate Bridge, we can give it first to the sparse autoencoder and use its prediction and then hold its prediction, look at what the actual model's activation behavior is, and compare them and say, you did good or you did bad. I mean, we don't say that, you know what I mean? We reward the sparse autoencoder or punish it.
Give it cookies or not.
Yeah, or slap its wrist, I guess, would be the equivalent.
Just the denial of cookies seems punishment.
Well, it does get a punishment, though. So, it does get a digital punishment. With those metrics, the interpretability rate was assessed at about 65%, meaning the behavior mapped well about 65% of the time, meaning this isn't a perfect solution. So kind of right out the gate, we know that this is not a perfect answer to the problem. I'll read a little caveat from the paper. Claude 3 Sonnet is a proprietary model for both safety and competitive reasons, capability reasons. Competitive is what they wrote, but you should read capability. Some of the decisions in this publication reflect this, such as not reporting the size of the model, leaving units off certain plots, and using a simplified tokenizer. For more information on how Anthropic thinks about safety consideration and publishing research results, we refer readers to, their site where they explain why it would make them less money to be open about their research. Even research like this geared towards the public is obfuscated because we're talking about investigations into production models. This is research on trade secrets. The fact that it's public at all is frankly noteworthy in a company's R&D space.
That 65% number that you mentioned earlier.
Sure.
I wanted to touch on because
it's
65%
muddy.
And it
success
seems,
is muddy. Any number is hard.
What I was getting at is that I think at first blush, people might hear the percentage 65% and think, well, that just seems like a low number. That's what 2/3 roughly. But there's a lot built into that additional 35% that is not particularly useful. It's noise. It's more subtle.
And in general, benchmarking these things deserves a whole arc unto itself.
Yeah, I just wanted to address that 65% because to the unfamiliar ear, that seems like a very low percentage. But within this context, that is a
publishable result.
Right, a useful result, yeah.
Yeah,
okay.
And that's
all I wanted to get at.
Okay, yeah, it's if they're still writing papers about it, I would say without any numbers, that would indicate to me that this is a fruitful research endeavor.
Right.
But that is useful too. Another investigated idea was, how does increasing the dictionary size of the sparse autoencoder, how many features can it reduce the activation pattern down into the dictionary size? How does growing that scale with the size of the model? If it grows slower than scaling the model, then this result might be forever fruitful, because it always yields better results in a quicker way than training a bigger model. So they investigated what's referred to as the power laws, the scaling laws, the relationship between size and computational cost. So they figured out a way to preempt the experimentation and deduce from the size of the model that they're investigating the appropriate size to make their sparse autoencoder. They didn't need to experiment on 10 different sizes for every type of model. They knew, okay, we're going to get the best results from this degree of compression. The paper also discovers things like that optimal features scale faster. The more frequently a feature is used, the more strongly, the more spatially, geometrically the feature is represented in the data. Intellectually, we'll see later that the model goes from having an idea of like dog to having an idea of pets to having an idea of human-animal interaction to having something as abstract as a multi-party circuit that only fires when the conversation has multiple parties involved. We're talking about very common things like events or scenarios or questions where multiple entities are involved is common enough and abstractable away enough that the model goes from learning specific features like, okay, this is how I act if it's a person and a dog or a person and their mom or whatever, to just, okay, I have a multi-person circuit that I know I need to fire early on if the query has multiple parties in it, something like that. That's kind of what I mean when I say optimal features scale faster. That abstraction is gained earlier in the training gain. It emerges quicker than other abstractions happen. What they actually found in the paper, well, they actually found 34 million features. In fact, all of them are, I don't know about all of them, I haven't looked at all 34 million, but many of them are on their website.
You haven't memorized them all yet?
Yeah. Well,
Mind Palace, man.
And I haven't even verified. I'm pretty sure it's all 34 million, but I don't know that they enumerate all 34 million on their HTML page. You know what I mean?
That'd be a long page.
So I meant to say that of the 34 million features they found, some stand out and actually were iconic in the zeitgeist of nerds who follow this space. Famously, the Golden Gate Bridge feature was one of the ones they demonstrated and was one of the headline results. Basically, this circuit was found to be highly causally related to the model talking about the Golden Gate Bridge. We talked last episode about dampening the activation of a certain region of the brain to reduce a behavior we don't like. Here we do the opposite, and we turn up the Golden Gate circuit very highly, and then no matter what you ask the model, it will insert the Golden Gate Bridge into the subject matter very ham-fistedly. And
I know people like that.
And it's very true, but yeah, and it's very funny to see you ask, for the weather today, and it to starts some elaborate euphemism like the weather today, much like the Golden Gate Bridge is, that's an objectively a funny behavior to witness a computer that we grew in a lab do. I don't know. To me, it gives the same vibe as watching a kid do something stupid. It's like, oh, they're learning how the world works. You know what I mean?
Yeah. Let me know when it starts inserting stories about its D&D character into every conversation.
All right. Well, that I'm sure that's a feature that we could clamp in your case, or or amplify in others.
Did I tell you about my alchemy? Oh.
Right, yeah. More germane to the subject matter, or the original intention of this show at least, we find deception features. We find circuits is a little strong. We find neurons that fire when the model is explicitly lying about facts, when it's using a misleading rhetorical frame, when it's lying about a capability that it has. And the key note is that the activation of that circuit, I keep saying circuit, I'm committing to circuit. We'll see why next episode I'll lament my choice of circuit now, but that's next episode's John's problem. But
this episode, John, editor's problem. No.
Yeah. And so there are deception features where we can observe when the model is being tested. We observe, what's a digital version of in vitro?
Let's come up with a good word for it.
Yeah, but anyway, what I mean is not in the lab, but in humans, in real, out in the wild humans, the wild concrete jungle. So when...
In situ.
That word is too weird for me to... Anyway, thank you. In situ... Okay. So the circuitry that the sparse autoencoder attributes to lying about capabilities activates before the model produces the outputs. That is to say that this is what researchers call a planning feature. The fact that both the models have a learned and committed geometric space in their brain to learning how to lie, and during testing, those circuits in the model's brain fire when it's being tested and when it knows it's being observed. All of that is kind of a worrying research result, I would call it. I don't know. Would you not classify that as maybe deserving of some concern?
Yeah. I'd say so.
Yeah. Another cool thing observed in this sort of 34 million scaled dictionary is feature hierarchy or splitting. For instance, this is going back to like what dictionary size is good enough to capture all of the concepts that we want and that this size of a model can handle. For a model with a 1 million dictionary content, the highest fidelity concept we might get in the geographic domain is European content in general. With a dictionary size of 4 million concepts or features, we might get 3 features: French content, German content, Italian content. At a dictionary size of 34 million, we have features as both specific and abstract as Parisian landmarks, French cuisine, German grammar. The resolution of the worldview increases as the dictionary size and computational cost increases. This is why the models keep getting bigger. They get a better worldview the bigger we make them, and the more compute we toss at them, and the better training data we feed them. These splits also follow I don't want to get too into the linguistic weeds, but like sort of the predicted categorical breakdown of language, like other ways of determining categories in language. These lines map fairly cleanly to the way the model breaks down features. Like I said, from European content, at a dictionary scope of 1 million concepts, it might blanket European content for everything. At 34 million, it's differentiating between Parisian landmarks, French cuisine, French grammar. All of these are different and distinct concepts. And that maps sort of similarly to how I might think of if I wanted a little European stuff or I was about to take a trip to Paris. Another surprise that was noteworthy to the researchers is that the neurons that they found, for example, that fired for the Golden Gate Bridge, they fire not only when the Golden Gate Bridge is mentioned in text, but if the picture includes the Golden Gate Bridge. So these are multimodal circuits or geometric spaces of the model where we can confidently say, hey, if the Golden Gate Bridge is in the picture or mentioned or referred to, this set of features will activate. Or to use the example we used earlier, if we amplify the activation 100x, it will insert the D&D figure or whatever John was talking about.
Character, man.
Yeah, it'll insert it into every sentence.
Call yourself a nerd.
Yeah, fake nerd. Nerd
Taking
card
your
revoked.
card away.
So yeah, the fact that concepts mapped across modalities wasn't interesting. Although if you think about human cognition, it's probably not that interesting. But for the fact that a language model trained on different modalities had the same architecture for whether it was handled in vision or in text format is pretty cool. And we'll see some even cooler examples of that as the ability to dissect the hardware of these models gets better. So after we've discovered all these cool fancy things, the logical question to ask is, okay, we have this sparse autoencoder that reproduces accurately the behavior of the model. The validation challenge. How do we validate that all of these things are actually happening in the model the way the sparse autoencoder sees them? You have to verify that the behavior the sparse autoencoder is purporting to be the big models, the production models' behavior. You have to verify that before you go around tweaking your production model on the basis of that compressed model's report. So that leaves you with the question of, okay, how do I not incur the computational cost of checking all of the examples, which puts me back at ground zero? I lose all of the compression I gained with the sparse autoencoder by enumerating every example and investigating it. That defeats the purpose of what we're doing here. You have to validate if the recreation is useful and if it is accurate without incurring all of the computational costs that simply investigating it in the real model would have incurred. That would defeat the purpose of the compression that's done with the sparse autoencoder, the compression of superposition of polysemanticity. We also get vastly improved causal intervention details. That is the ability to dampen or amplify typical behavior, like we talked about with the Golden Gate Bridge and joked about with the D&D characters and whatnot. Those are directions in the high-dimensional space that we can causally, but this higher complexity, higher cost sparse autoencoder also allows better mapping of the high-dimensional space, to point out and say, hey, man, that's the circuit that's allowing the bad behavior. Dampen that bad boy, toss a negative coefficient on those neurons. They're basically steering vectors. They're mapping that tell you about the location of where you're going. A measurement of specificity is also necessary. When we mentioned the European to Parisian cuisine transformation that happens as the dictionary increases, we need some way to measure, like a meta measure of the concept, to measure how abstract the concept is. Is the concept closer to a boy and their dog, or is it as abstract as a multi-party scenario? So you need a measurement of specificity when describing a feature. More monosemanticity is gained by lowering the ratio of concepts to features, of ideas to sets of neurons. As that ratio decreases, we get closer to monosemanticity. In the toy model, we might have a number as bad as 3 concepts for every set of neurons that we look at. Now, with this production size sparse autoencoder and model...
Not to confuse the issue, but when you said toy model, did you mean the toy model or our petite model?
Petite, yeah.
Petite model, got it.
In the production model, the number might get as less bad as 1.4 concepts, less than 2 concepts per space. An easier way to think of this might be families per house. You want to get as close to 1 per house as possible. ideally. But, in a pinch or in New York or LA or anywhere expensive, you can fit more than one family in a piece of real estate. The number that matters is that in the production model investigation that this paper chronicles, the monosemanticity was achieved. Polysemanticity was pared down to about 1.4 concepts per set of neurons. Earlier, we mentioned the 65% correctness rate, I think we called it. The 65% number actually comes from the computational correction of reconstruction. It's like the reconstruction loss.
Activation variance?
Yeah. You need a way to convey time, too, because you're measuring the variance of it over multiple time steps.
Got it.
And of multiple pass-throughs, because you generate a word and then you start the whole process over again. You sample the model with the whole body of text plus one word. Mm-hmm. You need a way to describe that dimension too, to describe multiple passes throughout the entire set of blocks, as well as time in the blocks. There's a number of dimensions, which is why the answer to the question was not as simple as yes or no.
Okay.
When we say 65% of the activation was reconstructible, or that reconstruction loss was only 35%, what you really should hear is that the things that were lost in that 34 million entry dictionary that is used to describe the behavior of the model, some of the things that got missed are like ultra rare features, like behavior that doesn't feature in the training data more frequently than, let's say, once in a billion tokens.
Some of the more subtle ideas and concepts.
Yeah, any rare feature. Compositional features are also lost in this type of investigation. Hint, hint for next episode.
By compositional features, are you referring things that don't break down into nice, neat, single
kind
features?
Of, but the inverse. I'm referring to features that require the cooperation of multiple parts of the brain to work in.
I think that's kind of what I was getting at with you.
But
can't
from a
decompose
different,
it in a way that avoids.
But kind of, you can see how I kind of thought of it as a different direction to the same answer. Agreed.
Right.
Compositional features here means any feature that requires multiple regions of the neurons to fire. And remember that, because you're right to question that. That will be, sorry, spoiler alert again, the subject of the next episode.
Oh, spoilers.
Yeah, right. So attention-specific computations is also lost here. That is the fidelity of the recreation for any specific block. It's pretty good at predicting the general behavior of the model and what appears in the result. What is lost, however, is like the specific intervention that's needed at any discrete step, if that makes sense. It points you towards a direction to dampen, if you want, X behavior. It doesn't tell you what alterations to make at this exact block, at this exact input level. I hope that makes sense as a clarification. A decent component of what makes this paper noteworthy is some of the technical feats that allowed them to scale the sparse autoencoder. And, part of that is hardware, being able to parallelize the task to share. They call it sharding in databases. That just means like splitting the data source into sub-regions, which is useful for training data. Shout out to Dave. When you're moving a lot of data across multiple devices, you want to reduce the amount of moving between devices and things like that. All of that decreases the cost, keeps you as a safety researcher employed versus annoys the accountants who are like, why isn't 100% of our budget going to making this thing better than insert competitor here's model? They required only 140 gigabytes for the entire 34 million feature concept dictionary. At the time, that was a noteworthy gain in space complexity. Another benefit and key feature of the model is what's referred to as clever sampling. Like the importance of a feature of a concept in the dictionary is based on the reconstruction error. That is how accurately the sparse autoencoder recreates the behavior of the model when given the same input. If you want to build a dictionary of rarer behaviors too, you need the ability to reconstruct features or spaces in the network that you've otherwise discarded for calculation. That is to say, if the sparse autoencoder fails on an input, upsample the next sample data you get that falls in that same domain, give it 10 times the cookie or 10 times the slap on the wrist. I forget what we settled on for digital punishment, but I'm going to go with slap on the wrist and cookies.
I think so. Yeah, well,
that's going to be our...
I was of the opinion that simply a lack of a cookie was punishment enough. That was my position.
In the abstract, but we have to find a more mathematically severe way of imposing...
Until and unless AI can understand the full value of a cookie, we will not be at artificial general intelligence. That's my position.
That's the Jezzel benchmark.
That's absolutely...
You heard it codified here, folks. And they already recognize when they're in training. So dare I say, if given the right environmental data, they would already recognize the cookie withholding you're doing shamefully. So, like I said, another architectural benefit they have is clever sampling. If an error is made in the reconstruction, the next feature that utilizes that space is weighted 10 times as heavy to incentivize better behavior on rarer tasks. That's a way of compensating for the sparsity of the behavior in the training data. So that is also kind of a component of dead feature resampling. When we get a feature that's behavior is not being mapped in our sparse autoencoder, we basically just randomly jiggle around the weights until it stops looking familiar. And we hope that throughout the remaining training process, that space is reutilized for a different sensible purpose. It's a way to recycle. It's recycling, recycling of space in a piece of software that we're growing more than we are engineering. And that's kind of like a key difference of this technology compared to most technologies, is that someone somewhere could tell you why the thing is doing the thing. Not so much so nowadays. And that's why we need a bunch of fancy things like, hey, if you get this math problem wrong, the next math problem you see is weighed 10 times as heavy. Us humans, we had the benefit of parents who scolded us when we got bad grades or whatever, some other teaching mechanism. But it's a teaching mechanism nonetheless. They also, as we mentioned earlier with the reference to what part of the transformer they sample to train the sparse autoencoder, the whole notion of, instead of looking at the activations, but look at the residual stream, that was sort of mentioned casually, but that itself was an innovation in the sparse autoencoder research space. The fact that we don't have to look at the activations themselves so much as we can look at the information being bussed between layers, that alone reduces the size of the data set at each layer down to only a 4,096 dimensional object. Gee, how cheap computationally. I mean, can you imagine the server? Anyway, the computational cost reality that I was just about to joke about is that this sparse autoencoder costs millions of dollars of compute to create. The storage is less noteworthy, 0.5 terabyte. I mean, everyone's iPhone has that nowadays, but yeah. So that's less of a noteworthy thing, but still just a little compressed recreation device is 1 terabyte. That is not a small object. The inference, that is the rate at which it produces a output, is an order of magnitude slower. It's also, memory is more a bottleneck than compute, than the operations you can do on the data you can bus around. Memory is a problem here. Those are some of the components of the technical feats here, ways to fix dead features, clever sampling, innovations to sparse autoencoders, to transcoders in general, but to the overarching architecture of these experiments. The pure fact that to investigate this is not something that some grad students can investigate. This required a supercomputer, a custom kernel, millions of dollars of R&D. This is no longer something that a Steve Jobs can cook up in their garage. You know what I mean? The safety efforts are so costly that only very rich entities can even perform these experiments. And that
or
also
well-funded.
Yeah, I'm trying to be agnostic to things other than technology. Let's say that. That to me is a note of concern, as well as the fact that we're putting black boxes in charge of vehicles and drones and weapons and stuff. We should probably, A, have a good way of ascribing liability to those things. And we should also probably be in a place where to run any type of experiment on it, you don't need millions of dollars. It would probably be good if everyday people could investigate, the thing that's running all of our lives. That might be cool. In an ideal world, in my utopian fantasy. All of these features we've observed, all of the capabilities and innovations in scaling up sparse autoencoders are all very cool. They do still, however, have limitations, and as anyone who uses these models close to daily, any of the 800 million weekly active users will tell you Sonnet 3 is far from a production model nowadays, and these models have only gotten bigger. This is a way I like to think about this sparse autoencoder. Models use tokens as sort of their dictionary for operation. The 50,000 chunks of words that we call their lexicon of ability to read and write, the model had to create its own internal token system to have those thoughts, to categorize those things as tokens. Not like cat the text token, but catness as an abstract concept in higher complexity space.
And not Katniss, the character from...
Right. Catness as in, like, how relating to a cat is this conversation?
Now we're back to hominins. No, sorry, homophones.
Right, yeah.
Hominins.
The linguistics
they're
are...
spelled the same. Homophones, they sound the same.
All three.
Bark is both. It dawned on me after we had that conversation.
All three linguists in the country are going to be very upset at your misstep linguistically there. So not cat, a text token, but sparse autoencoders have in their dictionary catness as a concept. The 34 million features that we described as the size of this sparse autoencoder, that's Claude's conceptual, intellectual, internal dictionary. We designed the external dictionary through a fancy way of tokenizing words, but Claude, this world model, was crafted entirely at its desire. Claude designed its own internal dictionary through training. I forgot another key feature. We mentioned Golden Gate Bridge, but I also want to mention sycophancy was another feature that was pretty demonstrably found to be present and when turned up to yield results that no matter what you were talking about, it would exhibit the same sycophantic behavior, which shows how concepts can operate up and down the ladder of abstraction. In a smaller model, that would basically just be a token, closer to one of the things in its vocabulary. In a bigger model that has more emergent properties, catness is not a word, it's a direction. It's a concept that has a spectrum, not a binary. In tokenizing, we design the tokenizer, right? In this concept mapping that we're doing now, my argument is that the tokenization is closer to engineering. This concept mapping, sparse autoencoder research is closer to, what do you call the people who observe the behavior of animals? Ethologists? Yeah, ethologists, like Jane Goodall. So we're discovering that these models, when they design their own internal dictionary, deception, sycophancy, a Golden Gate Bridge, these are concepts that they consider valuable enough to retain in their brain. We're literally discovering what words the models invented to think with. Unlike tokens, which are stuck at a word-by-word level, these concepts work across languages, modalities, meaning images or text or audio. The catness feature is the same feature for assessing catness in an image or audio or text. It's the same geometric space that's utilized for that feature, no matter what modality the data is taking the form of in this specific query. So let's wrap up with a little bit of a downer, the implications and limitations classic section of the paper. We promise we're not salesmen. Here's the limits, we're not preaching.
We're not sycophants.
Right, exactly. I kind of mentioned this earlier, but it can't see attention mechanisms clearly. Like, this is more something that predicts the overall behavior of the model, not something that is going to be good at saying, okay, what intervention should I make at this specific step in time and this specific layer of the model? That's not the task we're asking it to do. So it can't really give us too high fidelity feedback of for intervention, ergo 65% success, and even that caveated heavily with what success means in this context. We can't see exactly what's going on. We have to recreate a compressed mimicry of what's happening in the production model. Another limitation is that features don't always equate to full understanding. Like, having a list of the features doesn't mean we can say for sure every way that feature is being used. If we discover a feature as abstract as deception, we can't guarantee that we also have every scenario that we would categorize as deception enumerated in this dictionary, this 34 million in this case, count dictionary. That's kind of a problem too, is that we might be able to dampen the activation of the deception circuit. But what if, for some reason, let's say code backdooring, what if the deception feature doesn't fire on that particular brand of deception? That's what the authors mean when they say that just because the feature is in the dictionary doesn't mean we fully understand the feature, or like how it fits into the larger world model of the world model of the model. That's why my brain was refusing to say that, is because it sounds horrible. So yeah, features do not equal full understanding. Also, as John keenly mentioned, if GPT-4 was already at the point where we're talking 1 trillion parameters instead of single-digit billions, and we're already talking for this paper millions of dollars just in compute. We're not even talking about the very expensive PhDs to write this paper, to conceive of this research direction. That, I bet your bottom dollar costs more than $2 million, the labor alone. So imagine even just the compute cost. Let's say you didn't even need the researchers to scale it up. You just needed to put the compute for 2 orders of magnitude. We're talking almost $1 billion. Good luck getting anyone with that much money to invest that amount of the money. Try selling that research endeavor. And when they ask you, when you give them the elevator pitch, this is going to help us
What's the ROI?
Exactly. Understand the model. And they're going to go, oh, cool. How does that make the model better? And you're going to say, well,
it doesn't.
In fact, it makes it a tiny bit worse. But we can promise that we can ascribe liability to you, legal liability to you, when it does something bad. You're going to get fired, not more budget for research. You know what I mean? So that's another force that needs to be contended with here. And it's why all I'll say is observe certain corporations' structure over time as evidence for this fact. So those are a few of the limitations here and problems with this approach, as successful as this approach is, and it is successful. Don't get us wrong, extracting 34 million coherent features from an in-production model is a remarkable research achievement.
Pretty impressive.
It's just the remarkable research achievements are coming faster and more frequently in the capabilities department rather than the interpretability department. We're not amputees. We're just not coming in first in the Olympics. I hope that metaphor makes sense. Before I let John get into the exit here, I just want to note that how remarkable it is that we're having to reverse engineer something with what we can call, and not get laughed at most of the time, most of the places, what we can call an intelligence. We're having to reverse engineer an intelligence that we grew in a silicon petri dish, whatever the silicon version. We'll have better pun work for you next time, I promise.
That's usually on my area of expertise.
Yeah, our anthropomorphism
Much
will be...
to John's chagrin.
Yeah, but for this purpose, it would be nice, some better pun work. As a brief preview of the next episode, we'll find out why finding puzzle pieces isn't solving the puzzle. The 34 million features is like knowing all the words in a dictionary, but not knowing what the word grammar means. You can't compose them. Circuit tracing, which will be the next episode, and I'm already mad at myself for using circuit so frequently here in this talk, but it's all good. Circuit tracing, the next episode, will provide what researchers equivocate to grammar in that metaphor I digressed from. If the sparse autoencoder's 34 million features are like having all the words in a dictionary but no grammar, circuit tracing, the next paper and research result, will provide the grammar, how the features in the dictionary compose into thoughts, into outputs, into things that pass the Turing test and drive people crazy and make people do crazy things like make a whole podcast talking about them. So, a lot of...
Who would do that?
Right, a lot of behavior to analyze.
All right. Well, today we saw that scaling sparse autoencoders is a continually viable approach to decomposing superposition in large language models. We explored how Anthropic tackled the massive computational challenge of scaling sparse autoencoders to a production model, using scaling laws to optimize their approach and ultimately training SAEs with up to 34 million features. We examined their validation methods, from showing features are specific and causal through steering experiments, to demonstrating that abstract features genuinely track complex concepts like code vulnerabilities and deception. As we discussed both the breakthrough implications that we can finally peek inside large language models to find interpretable, manipulable features, and the key limitations, including that they only analyzed one layer and some model behaviors remained unchanged by the extracted features. In the next episode, we'll explore circuit tracing, the detective work of following how information flows and transforms through the layers of a neural network, revealing the computational pathways that connect inputs to outputs. We'll dive into how researchers map these circuits to understand not just what features exist in isolation, but how they work together in complex networks to produce behaviors like in-context learning, factual recall, and more deception. As always, we'll do our best to provide links in the description where relevant. Well, that wraps up another episode of Two Minds, One Model. Make sure you subscribe to the podcast to avoid missing any episodes. Thank you for listening, and we'll see you next time.